Hi everyone, my name is Celso de Oliveira, and today, on behalf of Sachin Tripathi, Mark Castaldi, and Dr. Ramesh Malla as a principal investigator, I will present our research project, which consists of preliminary material testing and analysis of two old railroad steel bridges. Presentation overview. In this presentation, we will start by understanding the general objective of the research. On section 3, I will talk about the specific presentation objective. Section 4 and 5, I will introduce the selected bridge and understand the research question. From section 6 to 10, I will present the material, testing methodology, results, and conclusions. On section 11, I will talk about the current and planned material characterization test, and to wrap up with acknowledgments and reference. Background and importance. As we all know that passengers and freight trains are important to maintaining a thriving economy, especially the Northeast Corridor, which expands from Boston to Washington, D.C. Maintaining a viable railroad system in New England is expensive and requires a constant infrastructure upgrade, improvement, and eventual replacement. Since the large percentage of the New England's railroad bridges are old, research is needed to better extend the safe life cycle of those old bridges, especially along the passenger route. General project objective. The primary objective of the research is to develop an efficient and cost-effective methodology for short and long-term structural response and condition health monitoring for new and existing railroad bridges. Material characterization, finite element model, field test will be used as a tool to achieve the research objective, which consists by determining the structural response. This presentation is focused on the tensile test from the material characterization phase. Presentation objective. The specific objective of this presentation are to present the strain stress behavior and the effect of different strain rate during the tensile test from the material of the selected bridges. Introduction. Bridge selection criteria. The first criteria for the bridge selection is the structure type, where the steel trusses and open deck was desired for the simplification purpose. Second, the bridge should be built using ASTM A7 steel, therefore should be built before 1940s. And to better understand the dynamic effect of the bridge, at least 100 feet span was an ideal structure. And lastly, the train type and the location help us to narrow the bridge selection. Based upon the mentioned criteria, Devon Bridge on Figure 2 and Costco Bridge on Figure 3 were selected. Devon Bridge. The bridge is located over the lower Housatonic River between Milford and Stratford, Connecticut, and it was built in 1906 by American Bridge Company. Devon Bridge have 7 span and it's a combination between deck girder, wire and truss, and Shizer rolling leaf bascule. The sample material are from the stringer angle from the web that was replaced during the renovations. Costco Bridge. The bridge is located over Mianus River in Greenwich, Connecticut, and it was built in 1904 by American Bridge Company. Costco Bridge have 12 spans and it's a combination between deck girder, deck trusses, and rolling leaf bascule. The sample material are from a bracing member of the adjacent pedestrian bridge replaced during renovations. With the background and introduction presented, it leads us to the research question. What is the current status of these more than a century-old railroad bridge materials? Materials. All the tensile specimens were milled from sampled material of the selected bridges. Figure 6 shows an example of specimens preparation using the CNC milling machine. The specimens are in dog bone shape according to the ASTM E8 specification. Figure 7 and Table 1 show the geometry and the dimension respectively. For this presentation, in total was tested 5 specimens for Devon Bridge and 6 specimens for Costco Bridge. Methodology. Test protocol. 2 testing machines was used for the tensile test. Figure 8 showed the 150 kilonewton at MET machine, and the figure 9 showed the Instrom machine. On Devon Bridge, 1 specimen was subject to a monotonic failure following the ASTM taste rate specification. The remaining 4 specimens were load and unload at a different taste rate and stress level through the failure. This process allows us to understand the effect of strain rates and study the yield region. Similar protocol test was adopted for Costco Bridge, with 1 specimen with monotonic failure and the remaining 5 specimens load and unload through failure. The table 2 shows the summary of the test parameters. ASTM A7 steel literature review. Since the ASTM steel was discontinued in 1967 and few mechanic study has been made, literature review was the first step. 2 documents were used for that purpose. The first one is the ASTM specification from 1939, where the yield stress, ultimate stress, and maximal elongation were extracted. The second literature is the Fritz laboratory report from 1963, where the yield strain, yield point, elongation, and the Young modulus were extracted. With that information, the table 3 was compiled, and the 3 main points represented on figure 10. The yield point elongation, and the ultimate point will be used as a baseline comparison with the test results. Results. Study of the elastic linear region of Devon Bridge. Sample 2 and sample 3 was loaded and unloaded using different test rate and stress level within the elastic region through failure. Figure 11 shows the stress strain plot of sample 3, where we can see the load pad for 10 KSI, 20 KSI, 25 KSI, and failure. Full elastic recovery was observed in sample 3 and sample 2. Sample 4 and sample 5 was loaded and unloaded to the plastic region to understand the plastic behavior of the material. Figure 12 showed the stress strain plot of the sample 5, loaded to 40 KSI, unloaded and reloaded to failure. Partial elastic recovery and strength hardening was observed on those samples. Tensile test, Devon Bridge. As we can see on the left side of figure 13, the tested material presents resemblance with the ASTM A7 steel, except the sample 1 which showed lower values. The right side of the figure 13 shows the insert of the elastic region, and we can observe that sample 4 and sample 5 doesn't show the yield shelf. Study of the elastic region of Costco Bridge. Sample 1 and sample 3 was loaded and unloaded using different test rates and stress level within the elastic region through failure. Figure 14 shows the stress strain plot of sample 3, where we can see the load path for 5, 10, 20, 25 KSI and failure. Full elastic recovery was observed in sample 1 and sample 3. Sample 4, 5, 6, and 7 was loaded and unloaded to the plastic region to understand the plastic behavior of the material. Figure 15 showed the stress strain plot of the sample 4, loaded to 35 KSI, unloaded and loaded to failure. Partial elastic recovery and strength hardening was observed for those specimens. Tensile test, Costco Bridge. As we can see on the left side of figure 16, the test material shows some resemblance with ASTM A7 steel, except the ultimate stress, which show lower values. The right side of figure 16 shows the insert of the elastic region, and similar to Devon Bridge, we can observe the sample 4 and sample 5 doesn't show the yield shelf. Specific observations. Effect of strain rate on test results. From 4 specimens from each bridge that were loaded and unloaded has shown that the strain rate does not affect the test results, as long as it's within ASTM specifications. Effect of number of testing on the test results. After the material gets loaded to the plastic region and unloaded, the yield shelf was not observed and the straight hardening was observed. This behavior is expected for most of the metallic materials. Conclusion and application. With the presented results, we can conclude that the test material has maintained their elastic yielding, plastic deformation, and strain hardening characteristics. With a limited number of specimens, Devon bridge material has maintained the ultimate tensile strength, while Costco bridge exhibit lower value in comparison with the ASTM A7 specification. This result will be applied to calibrate the finite element model and eventually use this calibrated model for different structural analysis. Similarly, the result will be used to establish testing protocol for fatigue analysis. In near future, additional testing will be conducted to support the results obtained in this presentation. Ongoing tests. Fatigue test. Specimen for force control fatigue tests are ready to be tested under elastic region. The test protocol will be defined by the ASTM 466 standard, and the ultimate goal is to create the SN curve, which will help us to estimate the remaining life of the material from the select bridges. Microstructure characterization. Specimens for microstructure characterization are ready to be analyzed. The test protocol will be defined by ASTM E1282, and the specimens will be analyzed before and after the failure. Acknowledgements. The research team extends its sincere thanks and appreciation to Transportation Infrastructure Durability Center at the University of Maine, the 2018 Regional 1 US DOT UTC for funding this project, Connecticut Department of Transportation for the continuing support, special for our technical champion, Mr. Dalokia and Mr. Dozier, Metro North Railroad Company for the support by providing the material and storage, special to Mr. Best, Maine Department of Transportation for the initial recommendation of exporting material testing. The research team acknowledgement goes to other New England States Department of Transportation for the continuing support, the University of Connecticut for providing the testing facilities, equipment, and financial support, special to Dr. Leak and Dr. Reddy for the direct support during the material characterization phase. References. Thank you for your time. Questions?